like 15 years ago or something, people would divide it into just two areas, supervised learning and unsupervised learning. Now I should say there's more classifications that are quite interesting. So I'm going to start there. We still do supervised learning. This is the bulk of the class. The bulk of this class is supervised learning. There's also unsupervised learning. I will cover this towards the end of the semester. It takes a week. Unsupervised. This is, we have K&N in supervised. In unsupervised, we have something called K-means. It's an algorithm. I'll explain how it works, but the intuition is similar to K&N, all right? Just what's the difference? Supervised, you have the X and you have the Y, correct? What do you think we have in unsupervised? Just the X. There's no Y. So we have to learn something about the data, but we don't correlate data to outputs. Do you guys see that? So, but it's got its uses, and I'll show you some interesting things that you can do it. I mean, it's a type of a classifier. It's just that it classifies whatever it wants versus, what you tell it to classify, because what it looks for is things that are similar. And you just tell it, I want 6 things that are similar. It's going to find 6 things that it thinks are similar, and it's going to give them to you, right? So it's sometimes useful, sometimes not useful. Does that make sense? All right, so the other one we're going to cover is something called reinforcement learning, RL, right? So we'll be covering this probably as soon as I finish neural nets. I'll throw that in. Shouldn't take that long. Reinforcement learning is very interesting because you learn by doing. So you build a model. Basically, the best place to think about reinforcement learning is games. But I should say, if any problem in the world that you can think of, if you can model it as a game, you can use reinforcement learning, right? And so the trick is this. Let's take a game for sure. And maybe in your 265, you may have already touched on this. I don't know, because that's an AI class. But, sorry? Pac-Man, so you guys did touch on it? Yeah. So basically in reinforcement learning, I'll do also like a game here just to kind of illustrate how that works. But in reinforcement learning think of a game, like the game of chess or, any game really, Atari, right? Your Atari games, if you've ever. So what happens in something like Atari basically, or chess, right? Let's think of Atari. You shoot and you destroy something, right? And then in another situation, you shoot and you don't destroy the thing that you were, let's say that's a destruction. So what the model, because it's playing a game, right? It knows what's going on. The game is keeping like a tally or a score that tells you, here you got a point, here's like a -1. Do you guys see that? In chess, it's the same, right? So if you lose a knight, bishop or something, you're in trouble. If you win one, you're up. So the game has these rules. You play it in a loop, basically. You're trying things out. And as you're trying things out, you're trying to learn what to do. Do you guys see that? So it's a type of supervision in the sense that the rules of the game give you feedback, either positive or negative. Got it? You take all these actions, you're shooting let's say you're in an Atari game and you're just stuck here shooting there, you're losing points, right? So the game is letting you know that. So you need to try something else, right? The key with RL is that you need to represent everything as states and actions, right? The easiest way to think of reinforcement learning is to create a table. It's where you should start. And the table basically tells you that on the left side, you have states, and on the right side, you have actions. Do you see that? And these values should be random initially, but as you're learning the game, you're learning what these values should be and which one you should pick. So you can think of it as a type of a weight. For instance, I'll give you this example. Let's say that this state represents somehow, and you got to really think really hard of how you're going to represent states, okay? And the easier the game is, the easier it is to represent the state. The harder, say, a self-driving car like a Tesla, that's a much more difficult state representation, okay? But possible, certainly. All right, so let's say that you're this space invaders, you're this ship, and you're stuck on this side, right? That represents that you're on this state. Do you see that? That state represents that you're here. So now the actions are what? In Space Invaders, what do you do? What does the ship do? Move left? Move right? Does it move back? No, right? It's always going forward, correct? Because the things are approaching it, so I assume they're... And what else can it do? Shoot. So you can shoot, not shoot, left, right. Do you see that? Are there any more actions for Space Invaders? Probably not, right? That's all it can do. So what you need to learn... Oh, yeah, please, sir. Yes, I would. I mean, because don't you in Space Invaders have a limit of how many bullets you can shoot? Yeah. Is that not a thing? So if that's a thing, that's certainly important. Because if you just get stuck here and fire all your bullets, you're done. You see that? So then, yeah, that's a good question. There's the fourth action. You just think of all the actions that you can take, right? So if you're stuck here, what's probably the best action to take? Go right. Do you see that? So since this is the state or represents this position, you know, this value, let's say that represents go right, should be what? High. And the other one should be 0, basically. So that every iteration, you look at the state that you're in and you pick the one with the highest value. In this case, because you're hitting the wall here, you should probably move to the right. Does that make sense? You see that? And eventually you pick up the other ones. You know, when you're in this state, you know, what's probably the state where you should fire? Just as an average, the most likely. It's difficult to say, but in the middle probably, because that might improve your odds if you're coming from the left or the right. Got it? So anyway, this is light neural nets right now, right? So I'm just throwing these ideas at you. We'll spend some time and take a look at the code on how to update this. There's something this is called Q learning. This is the Q table, and there's an equation that allows us to efficiently update these values, call them the weights, and that's going to be called the Bellman equation. So we'll talk about all that. We'll go over the code, and you can also, this is just a table. Q table is just a table, no neural net involved really, but we can also build a neural net to represent this. Why? The universal function approximation theorem says that I can approximate pretty much any function, including this. So I'm going to approximate it. Do you see that? All right. All right. Any questions on that idea? So that's, you know, right now I'm just talking about classification of ML. So we got supervised, unsupervised, reinforcement learning. It's a type of supervision, but you don't have labels, right? You don't have to actually go and create all this data. You just need to model your problem as a game and then find a way to get that feedback. You see that? I mean, this is like a nuts example, but if a Tesla has a bumper that moves, when it hits a person, that thing moves, right? That's a feedback that says you should not have done that. Do you see that? Obviously, that's probably you're going to get sued. You know? but you see that. So definitely with reinforcement learning, you have to do this in a simulator. That's the other thing. You need a simulator. Okay. But I'll show you, I have a simulator, for instance, called AI Gym, and we can model a lot of two-dimensional games. There are ones that do 3D games, or you can build your own, and I'll kind of give you some intuition on how that would work, okay? But as I said, after we get through neural nets, that will be the topic. All right, any questions on that one? So in your experience of knowing machine learning, do you know of any other classifications? You know, ways of classifying machine learning. So we got supervised, unsupervised, reinforcement learning. This is definitely an exam question, so better understand this. What's another one? Deep learning is basically, you can use it for supervised, you can use it for unsupervised. you can use it for RL, right? So I just said that you can represent this as a neural net because neural nets are universal function approximators. They can approximate a lot, if not all, everything, right? So, but can you think of a fourth categorization? Yeah. Ah, where did you get that? Yeah, okay, all right. Yeah, that's very good. Yes. Semi-supervised. Okay.
I think I heard you talk about it.
Did I? Okay, yeah. Semi-supervised. You're right. Yes. So what is semi-supervised? Anyone? Semi-supervised? All right. Have you guys heard of something called ChatGPT? It's all the rage, right? ChatGPT is a transfer learning LLM, very large language model. LLM. Yeah. That's Bing's AI, right? So this is based on this thing called GPT-3, which is based on GPT-2, which is based on GPT-1, which is based on a deep learning technique called transformers. Right? This is also based on an idea of transfer learning, but transfer learning is not semi-supervised. Transfer learning just means that the folks at Google or the people at Facebook, Meta, they train these models with huge amounts of data, super, GPU computers that have 16 GPUs in the motherboard, all working together at the same time. Computers that cost 100,000 or more, right? And ran this for a month, okay? To learn the weights, which is what we're gonna be, the perceptron also learns weights, right? The neural network that we're gonna build today, called a perceptron, or in this week, learns weights. ChatGPT is a transformer based on neural nets that also learns weights. We saw in Keras a few days ago that if you print the summary, you get the number of weights. Do you guys remember that? And I increased the size of the neurons and got like 32 million weights. I haven't checked what ChatGPT has right now, but it's probably in the billions of weights. You can Google it, and I'm sure it'll tell you the number of weights that it has learned, right? Meta, apparently, or Google, or both, have proven the following. That as long as you make a neural network that's bigger, so that means bigger architecture, and you feed it more data, it's going to perform better. That's crazy, right? Do you see what I'm saying? Like, I don't know how experimentally or if actually it's an extension of the universal approximation theorem, but they basically said these large language models, give them more architecture. That means make them bigger and give them more data and they'll get better. That's what they've been doing. They did they did GPT-1, gave it architecture, gave it data. GPT-2, larger architecture, more data, got better. GPT-3, more architecture, more data, got better. ChatGPT, I believe, is GPT 3.5.
Apparently, GPT-3 has 100 billion. GPT-4 is expected to have 100 trillion.
100 trillion. You see the jump there? That's like exponential or above. And basically, they're just saying the more architecture, the more data, the better. That's a problem for us because I don't have a computer or that amount of data to train my own GPT. So machine learning used to be in the hands of everyone. Anyone could do it. And now, unfortunately, it's starting to get to the point where only they, Google and Facebook, can do it because only they have the resources to do it. Yeah, go ahead.
So you're saying like even the hard.
Exactly. Well, what they're saying is you increase the architecture and you increase the data, it'll get better. That's what they're saying. That's, this is kind of, these are current things. So I can tell you this is what everyone's believing right now, which is surprising, right? They give it more architecture, more data. A GPU costs $4,000 to $5,000, like a GPU box with one GPU. what they have has 8 GPUs or whatever, special GPUs, hundreds of thousands of dollars. But even if you have, let's say that you're, you have wealth, right? And you can just spend on this computer for fun, you still need the data. Where are you going to get, I think Roberta XLM, which is the one I remember, was trained on 2.5 petabytes of data. That's a lot. I don't know what GPT-4 will be trained on. Probably a lot of data.
At what point does quantum computing start?
When it's invented, doesn't exist.
2 days ago, super big.
They're making breakthroughs. I agree, but quantum computing, I think, can only solve specific problems. It's what my understanding. Someone else may know, but I don't know much of it. But my understanding is it can solve specific things.
It obviously the computer the layers of quantum bits, which two, like you can have 2 quantum bits and bits connected more. But
yeah. No, yeah. I always think of it as, whereas we need as we will learn, gradient descent, right? Gradient descent can't. So let me put it this way: we need weights, correct, to have a model. I mean, in theory, we could just randomly select weights forever until the model improves. What's the problem with that? Selecting weights randomly is probably not a good idea. We don't do that, thankfully. We have something called stochastic gradient descent. Is an algorithm that does what? Intelligently selects how to update the weights. Do you guys see that? That's what we will be learning about. It's a very important thing. Without it, we would not be able to do machine learning. To take this analogy to your question of quantum computing, maybe quantum computing, because of all this computing power, could guess all the weights in one shot and see which one does better. Do you see that? But I don't know how close we are. It's one of those technologies where we're only either 5 years away or 50 years away or 100 years away. It's not clear. Okay.
Apparently, GPT-3 was only trained on a little bit less than 600 gigs.
600 gigs of data. GPT-3?
568.
Yeah, it's possible. I mean, but they're getting bigger. So anyway, so going back, so I kind of got away there. So semi-supervised, right? That's what we were talking about. So the question is, you have to give these large language models, right, 2.5 petabytes of data. If they were fully supervised, what does that mean? We would need to give it the text, right? Because it's a language model, so it's learning text. And we would have to train it, right? We have to give it the X and the Y, right? Imagine annotating all of those sentences with labels. That would be impossible. Do you guys see that? But at the same time, semi-supervised means we do have this and we have that. So then how are we getting this in correlation to that? Do you see that? That's semi-supervised. We do have it. Basically, we do have it, but it's not difficult to get. Like regular supervised learning, you think, iris, setosa, virginica, you have to look at those plants and label them, right? That's supervised. Semi-supervised, we still have X and Y, but we don't have to label it. So how are we getting it? Well, as it turns out in language, it's easy to get because we have a lot of language. So I have the cat is sleeping on like that. You see that? So this is the input. This is the neural net, right? The transformer. And the output is the cat is blank on, and then I could say the bed. Oops. On the bed. Do you get how it's semi-supervised now? Guys? This is the input. this is the output. So this is the X, this is the Y. What it learns to do is what? Fill in the blank. So think of it this way. The cat is sleeping on the bed and it predicts the cat is, well, eating, I guess, could be correct, but it's got a lower probability. The cat is flying on the bed. That's not correct. Do you see that? But when we do the training, we gave it millions of these sentences, right? And so it's going to learn that it's more likely that it should be sleeping. Do you guys understand? Is this easy to get? Yes. I mean, it's literally the same sentence. So we give as input the sentence, and we give the Y also the sentence, except that we take out words. So that the machine learning algorithm needs to learn that word. That's semi-supervised. There is an X and a Y, but it's something easy to get because we give it the same thing as both input and output, where the output is missing. It's got blanks. And so it's basically doing fill in the blank. Any questions on that idea? All right, so that is semi-supervised. So in semi-supervised, we do have X and Y, but they're easy to get, right? Like in text, for instance. All right, so anyway, that's the classification of neural networks. Okay. So for neural networks, as I said, this is just light and terminology. So what are the algorithms involved? So the algorithms involved. All right, so what this means is, to implement neural networks, which is basically what? A neural network is an architecture set of neurons, other neurons, right? What we need to learn is the values of these, the parameters, right? The weights. That's what we need to learn. And that's why we're going to start at the perceptron this week, because it was basically the very first neural network in a sense. And so we're going to go through the whole process of how it is trained, and it should be able to classify, actually. Okay, right? And that should give us a lot of the intuition. But to do that classification, and in particular, the classification of deep neural networks, there's an algorithm called gradient descent. It's actually called stochastic gradient descent. Okay, this is something that we will talk about later, stochastic gradient descent, but it's a very important algorithm. Without it, it would not be possible to train neural networks. Okay, there's a very interesting, interesting technique, right, of how it works, but also very mechanical in how it does what it does. Okay, and that stochastic gradient descent actually has several algorithms that were invented for it to work. Right, we're not going to get into all that depth. Also, I should stress, even though we're going to discuss this and we will do some examples, the reason why PyTorch and TensorFlow were invented is so that we don't have to do this. So this is the one part that those frameworks actually abstract completely from our view. We just kind of have to learn how to code it, but they actually do that whole processing. Okay, so stochastic gradient descent is done by TensorFlow and PyTorch efficiently, very efficient. All right. However, as I said, we will cover, the elements of the algorithm, which are not super complicated. Okay. Any questions there? All right. So there's going to be this idea of the feed forward algorithm and then the back propagation algorithm. All right, that implement all of this. And at the end of the day, everything in machine learning revolves on guessing these weights, or not guessing, but actually optimizing for these weights. Got it? All right, so we will look at that. So that means we're going to need to have several steps, including a little formula that allows us to update the weights, which is called the update rule. And we will talk about that. But just as I said, just to kind of give you an introduction, we have the weights, right, that we want. And then we have the current weights. And then what we do is we need to update them. So what we do is we take what is called the learning rate, which is a value that we multiply times another value that we get, which basically gives us direction. So what that means is every time we're updating the weights, we need to know if it's a plus or a minus multiplied times some value that you choose. And then what's going to be the effect of that on the weights? If we do something like this, I'm just generalizing it right now and not telling you how to compute it, but this is how we update the weights, right? So what are we doing here? Every iteration, if we get a positive times this, what happens? Huh? Decrease, right? Is what you mean. You decrease the weights. What if it's the next iteration, it's a negative? We increase the weights. Do you see that? So this is the little game that we're playing, right? To update the weights. We don't just randomly pick, oh yeah, I'm going to add any and see what happens, because that would affect the network. Instead, you have the weights, and then you decide that you're either going to decrease or increase the weights by a specific value. This is really important. If you pick 0.000001, I can tell you it'll never find the weights, because you're increasing or decreasing the values by too little. You see what I'm saying? The other thing can happen is if you make that too big, it never quite arrives at the good values, because it's the changes are just too drastic. Do you see that? All right, so all of this will be studied within the context. We're going to basically do this several times as we go through the perceptron, linear regression, logistic regression, multi-layer perceptrons, and deep neural networks, okay? So we're going to, but it's always the same mechanism. And all of those are only different in the architecture, which means this, right? How many inputs, how many hidden layers, how many outputs. That's called architecture. But the mechanism is always to do this. To go back to your quantum computer thing, we wouldn't have this. We would just do all the pluses and minuses in the universe, but that can probably be a lot, right? But if a quantum computer could do that in parallel, you don't need stochastic gradient descent. But until we have that, we can't do that random. So we need to do it in a smart way. So the question is, if this is fixed in mostly, how do you decide if it's plus or minus? Do you see that? That we have to study how this is done, okay? This is the stochastic gradient descent algorithm. And like I said, the proof that I'm asking you to do is bonus points will also relate around this idea, okay? But I have to give you a lot of background for you to kind of get what we're talking about. Do you have any questions on this? Pretty easy, pretty clear? All right, good. So that's kind of where we're going. So we'll talk about that. But as you probably understand by the intuition or know this, what happens here? You have some inputs, they go through the network, and you get some outputs, correct? Yes, and this is, let's say, a hidden layer. So you get some inputs, they go through the network, you get an output. What's going to happen if you have really bad weights? Get bad outputs, right? That's kind of what happens. What do you do with these outputs here? If you haven't learned, what should you do intuitively with the outputs in a supervised learning problem? Compare them to the real values. Do you have real values? Yes, right? That's the whole point of having a train set. And when you have so let's say you have the pred, either a vector or a value, and the real, what do? You take the difference, generally speaking, right? So if you get a 0.5 here, and then you get a 0.8 over here, that's a difference of 0.3. What if you guess 0.01 and this is 0.8? Which one of these is a better prediction? Huh? The top one, right? Because it's the one closest to the real value. Do you guys see that? So that's what we do in machine learning. We predict, we compare to what we have. We take some metric, some measure, of closeness or whatever you want to call it. And then based on this result, which we'll study this in more detail later, we back propagate. Back propagate. So that answer back propagates to update the weights, which is this equation. Do you see that? But this difference has to work itself into that somehow, right? And that's requires a little bit more. Do you see that? But that's how it works. It's simple. I mean, it's actually pretty simple, right? You know, what happens in the next iteration? Take the input, feed through the network, get some outputs, compare the real ones, get some kind of a difference or something. Then maybe there's something in between, but feed into this, update the weights. So obviously, this result has to help you to decide how to update the weights. And once you do this, eventually these weights will be pretty good. These predictions will be almost exactly like this. And then the weights change very little and your model is trained. Got it? All right, that's the general mechanism. All right, so we will take a look at that later. Okay. All right, so now we're ready for the history. Okay, so we're going to talk about the history. This is really, I think you'll find this pretty interesting. I'm only going to do history today, but pretty nice history. Okay, so